Hello, everyone, and thank you for joining us today. Welcome to Megger's monthly Testing Tactics webinar series. Today's topic is medium voltage and high voltage cable fault location utilizing arc reflection method. My name is Michael Fleischer, and I'm the digital marketing specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. All webinar attendees are eligible to receive one NIDA CTD and one PDH or 0.1 CEU for attending. You will receive this in an email within 2 business days of the webinar. That email will also include a copy of the PowerPoint presentation and a link to a video recording of the webinar if you'd like to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered at the end of the webinar during the Q&A session. Our presenter today is Javier Ruiz, Area Sales Manager. Also, to assist with the question and answer session, we will have 2 panelists joining us today. Henning Oetjen, Product Manager, and Robert Probst, Product Manager. All right, let's go ahead and get started. Thank you for joining us today, Javier.
Thank you. Okay, thank you. Good morning, everyone, and thanks for attending to this webinar. I would like to start reviewing quickly the agenda. First, we'll go to talk a little bit of cable fault location considerations. Then we will review what we call the old-fashioned cable fault location method. Then we will continue talking of medium voltage cables, cable construction, type of insulations, type of concentrics, voltages, what parameters are involved in the cable fault location, and the typical faults for medium voltage cables. We will continue talking of the cable fault location procedure, and we will analyze each of the 4 steps: the safety, the checks, the prelocation using the arc reflection method, pinpointing. Then we will do a brief summary of the arc reflection method, and we will see an example of a fault location in a high voltage cable of 230 kV. And we will finish this webinar doing a simulation of a cable fault location using the tray products. So let's start with the cable fault location considerations. Of course, the objective is to find a fault in an underground primary cable, and the challenges that we will face are find it safely, find it quickly, and it will be a troubleshooting process in which we will use a toolbox of various techniques. So the solution will be apply orderly, effective methods that will be outlined on the following slides. Talking of the old-fashioned cable fault location method, consisted on connect a jumper to a faulted cable. Then we turn the voltage up to the maximum, and we started to send in high voltage pulses on the faulted cable. And then we walk the cable route to here, fill the fault, or locate it with an acoustic device. So this method has clear disadvantages because it's inefficient, damaging, and unsafe. It's inefficient because it requires time and manpower in long cable runs or deeply buried. For instance, let's consider that we have a 1-mile cable and we have the fault 26 feet before the far end. If I have connected my source wave generator or my jumper at the beginning, at the near end of the cable, that means that I will need to take a long walk to find the fault. For this reason, we said that it requires a lot of time. But the worst scenario is when I cannot find the fault when unknowingly we are thumping on a dead short. Let's say that the fault that my cable has is a short, which means that I have in contact the center conductor and the concentric. If I have a short and I send a high voltage pulse through this fault, I will not have an arc. Then no bank can be here because fault cannot flash over. So this is maybe one of the worst scenarios with the old-fashioned cable fault location method. It's damaging also because extended thumping may damage good segments of the cable, and it's unsafe when tamping on cable with corroded concentric, for instance, unjacketed cable, then the high voltage return may find its way through the soil back to the tamper and may cause build-up of dangerous set potential. So for the reason, we don't recommend the use of the old-fashioned cable fault location because it has all these disadvantages. So the question is how to avoid falling unknowingly in these traps. Well, the first that I want to know is what kind of fault is in my cable. Is the first information that I would like to have. And the second one is to confirm that I am connected to the correct cable. So it's important to know that to avoid falling in the traps that we saw in the previous slide. So the assess of what kind of fault exists is very important. If I have an open conductor fault or a low resistance fault, or for instance, a pinhole fault, that means a high resistance fault. Also, it's important that I confirm that I am correct, I am connected to the correct cable. This means to the cable that has the fault. So to perform assessment reliably and efficiently, the TDR, the radar, is the solution, and the method associated with is the R reflection method. Well, let's talk about medium voltage cables. If you see the picture in the slide, you will see that is the classic construction of a medium voltage cable, in which we have a conductor that could be of aluminum or copper material. Then we will have this semicon layer that is the conductor screen. Then we have the insulation that in the case of this slide is a solid dielectric insulation and EPR insulation. Then we have another semicon layer that is the insulation screen. Then we have the metallic shield. In the case of this picture is a tape shield concentric. And finally, we will have the jacket. Of course, that we can have difference in our medium voltage cables. As I said in the previous slide, there are unjacketed cables that have no jacket. But more or less, I will say this is the classic construction of a medium voltage cable. Continue with the cable construction. We have, if you see the picture in the left, the classic one core or one phase medium voltage cable, in which we have, in this case, in this picture, a conductor, a center conductor of copper material. Then we will have also the semicon layer, the XLP insulation, and the concentric. In the next picture to the right, we have a three-core cable, but in this case, each phase has its individual shield. If you see each one of the cores, each one of the phases has its individual shield. And in the next picture to the right, we have one more time a three-core cable, but in this case, the three phases share a common shield. So it's very important from the fault location perspective that we know the construction of our cable. Not only because of that will depend how I will connect my tamper, how I will connect my source wave generator. It's also important because depending of the cable construction is where may the fault occur. For instance, if we consider the 2-3 core cables that we have in this slide, in the first picture that is in the left, we have a 3-core cable with individual shield each one. In this case, the fault may occur between any of the 3 cores and its individual shield. Okay, because the distance is the lower one. But if we consider the other 3-core cable in which we have only one common shield, the fault may occur between the conductors, but also between any of the conductors and the concentric or the shield. So for the reason, it's very important that we know how is the cable constructed. So let's move and talk a little bit of cable insulation. For medium voltage cables, the most common insulations that we have in medium voltage cables are the solid dielectric insulations, also we call plastic insulations, or more properly polymeric insulations. In this case, we have the EPR and the XLPE. And the other type of insulations is the paper. We have paper insulated cables. In terms of allocation, or from the perspective of the allocation, the type of insulation makes a difference. Let's consider that I have a XLPE cable and that I have a fault in that cable, and the fault is a pinhole fault. Then if I have a pinhole fault in an XLPE cable, the hole in the fault will be filled with water or air. If I have a pinhole in an XLPE cable, the hole in the fault will be filled with water or air. But if by the other hand, I have a paper insulated cable and I have also a pinhole fault, the fault will be filled with oil, and the oil is a dielectric, which means that I will need more voltage to break down the voltage of the pinhole fault in a paper insulated cable, and also I need more energy to sustain the arc in that fault in comparison with the other insulation that is the EPR or the XLP. So the type of insulation makes a difference in terms of the cable allocation. Now, talking of the cable neutral or concentrics, we have the standard concentric that we see the picture in the left. In the middle, we have a tape shield cable, and in the right, we have unjacketed. We see an unjacketed cable. There are some of the type of shields or neutrals that we can find in medium voltage cables. So continue with the voltage of cables. Normally, we used to talk of a 15 kV cable or of a 35 kV cable, but that is the voltage between the phases. For fault location, what is important is the voltage between the center conductor and the concentric or neutral. So if you see, we have that for a 15 kV cable, the phase to ground voltage will be 8.6 kV RMS. For a 25 kV cable, the phase to ground voltage will be 14.4 kV RMS, and for 35 kV cable, that voltage will be 20.2. Of course, this voltage are if the cables are okay, but if I have a fault in my cable, the breakdown voltage expected will be lower. In other words, if I have a faulted cable, the breakdown voltage will be the air gap distance in the fault. Okay, so let's talk of the cable parameters. The first parameter that I would like to talk is the cable capacitance, and the cable capacitance in a cable depends on the material of the insulation. For the reason we have here the epsilon, that is the permittivity of the material of the insulation in my cable. Then I will have the length of the cable also. It's important for the capacitance value of my cable. And finally, I will have the ratio between the outer radio and the inner radio of the insulation. The three parameters that I mentioned is what drives the capacitance value of my cable. So is for the reason is that is important to be aware of that. If you see the table that we have in this slide, you can see that it looks like the capacitance increase the capacitance decrease as we increase the voltage of the cable. But what really drives the decreasing of the value of the capacitance is the geometry, the ratio between the outer radio and the inner radio in the cable. And also it's the same if you see for the same voltage. Let's consider the cable of 15 kV. As we increase the size of the conductor, you will see that the value of the capacitance also is increased. But one more time, this depends of the geometry of the relation between the outer radio and the inner radio in the cable. The next value I would like to talk about is the cable impedance. This is also an important parameter because the TDR will measure is the change of impedance in my cable. And we could say that the change of impedance of my cable is in a function of the distance between the center conductor and the concentric. So for the reason the change impedance is very important for the cable fault location. The other important parameters is the cable velocity or the propagation velocity, which is the speed at which a signal travels down through the cable. In the case of fault location, the TDR will send low voltage pulses, and that pulses have a speed or travel with the speed of the light. But when the pulse go into the cable, this velocity will slow down, and this velocity will be between the 60 and the 70% of the speed of the light. And the cable velocity will be affected by the insulation material, the conductor size, and the insulation thickness, and could be also the manufacturer and other aspects can affect the cable velocity. If you see the chart that we have in the slide, you can see that we can have the propagation velocity of the cable velocity in meters per microsecond, fits per microsecond, yards per microsecond, or also as a percentage of the speed of the light. And you can see that what really drives or really changes the propagation velocity is, as I said, the insulation material, the conductor size, and the insulation thickness. So this is the last parameter I would like to talk. Talking of cable faults, I will fault on medium voltage cables is the pinhole fault. This one is a high resistance fault, typically in the order of the kilo ohms. It's a high breakdown. This fault has a breakdown voltage, typically in the order from 4 kVs to 8 kVs for 50 kilovolt cables. It's a fault that has a high breakdown voltage. And in this fault, the center conductor is continuous, but is not in contact with the concentric or neutral in the point of the fault. The next fault I would like to talk is the open conductor. And this fault, the open conductor fault, is very common when we have cables with center conductor of aluminum material. In this case, what happens is that the fault current has burned and opened the center conductor. So we have an open conductor because the fault current has burned and opened the center conductor of aluminum in my cable. And in this kind of faults, the TDR cannot see past this fault, and looks like it's the end of the cable because we have an open conductor. And we can think one more time that the pulse of the TDR will walk with one leg in the center conductor and the other in the concentric. As far as I have continuity in volts, the pulse of the TDR will go through the cable. But if I have no continuity in my center conductor or in my concentric, the pulse of the TDR will stop right away. So in this open conductor fault, we may not be able to use the R reflection method if the conductor is burned back. if the conductor is burned back, may not be able to use the R reflection method. So what we need to do is go to the other side and try it again. But why? What difference makes in an open conductor fault do the fault location from one side or the other of my cable? I will explain this with this picture that you can see here. We have the substation, we have an underground cable that goes to a riser pole, and let's say that this is a cable with aluminum conductor, and the fault that we have is an open conductor fault. So what happens is that from the side of the substation, from the side of the source, the energy uh, will burn back my conductor. So if I try to do the fault location from the side of my substation, I will need a higher voltage to break down the air gap between the center conductor and the concentric. But if I move my tamper to the other side, to the side of the load, to the side where I have the riser pole, if you see in the picture, you can see that the air gap between the center conductor and the concentric of the shield are not so big. So in this case of faults, we need to see from what side is better do the fault location. Okay, let's continue with the next fault, that is the short. In this case, when we have a short fault, what means that we have in contact the center conductor of the cable and the concentric. And what happened is that during the fault, the insulation was melted. Other example of a short could be a ground rod or stop sign through the cable. When we have a short, we consider, well, the short is a low resistance fault, typically in the order of less than 100 ohms. And also, one more time, the TDR might not be able to see past this fault. And once again, if we think or we consider that the pulse of the TDR will walk through the cable with one leg in the conductor and the other in the concentric, if we have a short, there is no way the pulse of the TDR past this point. So TDR might not be able to see past this fault. The tamper will not produce a noise because we have a short. If we have a short and we send a high voltage pulse, there will not be bang. So we cannot use the tamper to find a fault in a short, to find a short fault. And we cannot use the reflection method for this reason, but it's not necessary because if we have a short in the cable, we will see in the trace of the TDR downward blip, and we will know where is the fault or the short fault in my cable. Well, talking of, I would like to talk a little bit of underground residential distribution systems, or URD systems, because in this type of cables, we can use in very successful way the R reflection method. For URD systems, the R reflection method works perfectly because normally we have cables with insulation that will be XLP, E, or EPR. The system voltage are 15, 25, and 35 kVs. Normally, we used to have point-to-point topology. The cable goes from point A to point B. We don't have branches, which is very good for the TDR. So it's ideal for TDR-based techniques as the R reflection method. And in this case of systems, we can use portable tampers. So for the reason, it's very, very nice to have the R reflection method for these URD systems. Now I would like to talk of the procedure for the cable fault location. If you see in the slide, we have the 4 steps that we need to do to find the fault. The first is always the safety. And in terms of the safety, we need to follow the rules of the company. Always we need the first, always safety first. Then the next step, the second one, will be the checks. And in the checks, I want to learn 2 informations. The first one, which one is the faulted cable? And the second one, what is the breakdown voltage of my fault? Then I will move to the third step, that is the prelocation, in which I will use the TDR and also the error reflection method. Indeed, the error reflection method is a combination of a TDR and high voltage. And once I prelocate my fault, I can move to the last step, that is the pinpointing of the exactly location of the fault. Let's start with the safety. And in the safety, that is the first step, as I said, we always follow established company work rules and procedures. And we need to ensure, before to do anything, we need to ensure that the cable is de-energized and grounded. What we want to do is avoid the risk of backfeed, because the backfeed voltage could damage to the personnel and the property. And the last point that I want to keep in mind is the three sources of hazardous voltage. And the three sources of hazardous voltage are the operating voltage, the induced voltage, which means the charged cables around of my fault location place. And the last one is the test equipment, which means the tamper. So continue with the safety. It's very important that for the fault location, we have a single point grounded, one system ground only, one system ground only. So this is very important for the fault location. And also we need to be sure that we have a through earth ground, and the order of the connections will be, if you see the picture in the left, the first connection that I will do is the safety ground. Then I will connect the test lead return, is the second connection that I will do, the test lead return. And the last connection I will do is the high voltage connection. So this is the order of the connections when I do fault location. First, the safety ground, then the high voltage return, and then the high voltage connection. Now, talking of one system ground only, if you see the picture in the left, you will see that we have that situation. In the picture in the left, you can see that the concentric potential is the same that the potential of my safety ground. So in this picture in the left, we have the same potential for the concentric of the cable under test and for the safety ground. And this is what I would like to have when I am doing fault location. If you see the picture in the right, we don't have the same situation. In the picture in the right, we have that the concentric or the neutral of my cable is not at the same potential that the safety ground of my tamper. So what could happen in this case is that I can have a step potential. And if I am the guy that stand up in the middle, I could suffer a step potential discharge. And this is something that I want to avoid. For this reason, it's very important that we have the condition that is shown in the picture in the left, one system ground only. Let's continue with the second step, that is the checks. And as I said previously, in this step, I want to learn two distances. The first one, in the checks, what I want to learn is two informations. The first one is what is the faulted cable, which one is the faulted cable. I want to confirm which cable has the fault. And the second information that is very important is the breakdown voltage of my fault. These are the two informations I would like to learn during the checks process. We can do the checks using the insulation resistance measurement or measuring the cable, or also we can use the high potential test. And when I am doing the high potential test, there are some questions that I will answer during the process. For instance, can the cable hold voltage? Is it the correct cable? Is there a short? Can I use the error reflection method? For instance, let's say that I'm doing a hypo test, and I have no idea what fault has my cable. So I will do the hypo test, And what I see is that I cannot charge my cable, which means that the needle of the voltmeter in my tamper will not go up. Okay, so I cannot charge the cable. Then how I will answer the questions? Well, the first one, can the cable hold voltage? No. Is this the correct cable? Yes, certainly it's a cable that has a fault. Is there a short? Yes, because the cable cannot build up voltage or cannot hold voltage. And can I use the error reflection method? No, because if I have a short, I cannot dump in a short. So for the reason, it's very important this step, the second one, that is the checks, because will provide me with important information. And the last one, the last point in the checks, of course, is if I have no idea, if I have no clue, well, where is the path of my cable? Well, I will do a tracing to get the information regarding the path of my cable. So let's continue with the third step, that is the prelocation. As I said in the first slides, the prelocation is pretty much like a toolbox in which I will use the best tool for the fault I have in my cable. In the case of this webinar, I will talk only of two tools, the TDR and the error reflection method. Okay, so let's start talking of the TDR, or also we call time domain reflectometry. The TDR for cables work under the same principle that the radars in the airports. What the radar in an airport will do is that will measure the time that will take to the pulse go from the radar to the plane and then go back to the radar. Is what the radar will do. Will measure the time that will take to a pulse go from the radar to the plane and then go back from the plane to the radar. And if we know the propagation velocity of the pulse in the air, we can get the distance to the plane. Well, in the case of the TDRs for cables, the TDR also will send low voltage pulses, and the pulses will be reflected when we see when the pulse will see a change of impedance in the cable, a change of impedance in the cable. So what we will need is two parallel conductors, that in the case of the medium voltage cables are the center conductor and the concentric. For sure, we need to consider the signal speed or the propagation velocity of the low voltage pulse into the cable, and the impedance of the change of the impedance will be the change in the distance between the center conductor and the concentric. For instance, consider the distance between the center conductor and the concentric in a medium voltage cables. That distance will change if we have a splice, also will change if we have a transformer, and of course will change if we have, for instance, a fault like a short or a pinhole. Then with the TDR, we will look for change of impedance. Continue with the time domain reflectometry. You can see in this slide that we have different traces for the different change of impedance. For instance, if we don't have any change of impedance, what we will see will be a flat line, as you can see in this picture. If we have, for instance, a high impedance change, for instance, an open conductor at the end of a cable, we will see an upward blip. As you can see in this picture, we can have an upward blip. If we have, for instance, a low impedance change, for instance, a short between the center conductor and the concentric, we will have a downward blip, as you can see in this picture. And if we have in the cable splice or transformers, what we will see is this characteristic reflection that we can say that is a combination of the previous two, in which we will have first an upward blip and then a downward one. So this is the characteristic reflection for a splice or a transformer. And then in this slide, you are seeing the typical trace, the typical low voltage trace of a TDR. This is the classic typical trace of a low voltage trace. And if you can see, with the low voltage trace of a TDR, we can see only two change of impedance in clear way. The change of impedance between the test leads of my tamper and the cable under test. This is the change of impedance that we have at the beginning of the trace. At the second change of impedance that we can see very clear is the end, in this case, the end of the cable. But if I have, let's say, a pinhole fault, will not be possible to see that fault with the low voltage trace. So what I need to use is the R reflection method, and is the next step that I will, not the next step, the next method I would like to talk, the R reflection method. So prelocation, we are still in the third step, and we need combine the low voltage trace and the high voltage trace. So the R reflection method, it's a two-step process in which we will combine the low voltage trace from the TDR with the high voltage trace coming from the tamper, let's say, or the high voltage coming from the tamper. And in this case, we will overlay the two traces. So we will have the blue trace of reference measurement plus the source measurement of red trace. And we will combine the TDR and the source wave generator or tamper. Is what we will do. And what we will do during the R reflection method is that we will, with the high voltage pulse, we will create an electric arc at the fault position. And this arc will have a duration of milliseconds, good enough in order the live TDR pulse bounce back. And then the live TDR pulse will bounce back and will show us a downward signature. That means we have a short, because when we have an arc in the fault position, what we have is a temporary short between the center conductor and the concentric. So let me explain this a little better with the next slide. Let's consider that we have a medium voltage cable. Let's say that it's a cable of 15 kV, and we have a pinhole fault over here. And this pinhole fault needs at least 4 kVs to flash over. That means that the breakdown voltage of my fault, of my pinhole fault in this cable, flash over at 4 kV. That is the breakdown voltage, 4 kV. Well, the first that I will need is use my TDR in my tamper to get the reference trace. And this is the reference trace. In the reference trace, I will have to change of impedance. The change of impedance from the coming from the test leads and the connection of the test leads and the cable under test. If we see this reflection, this change of impedance comes from the change of impedance between the test leads of my tamper and the connection between the test leads of my tamper and the cable under test. So this is the first change of impedance. Then the low voltage pulse will walk, let's consider, with one leg in the concentric and the other in the center conductor. What will happen with the low voltage pulse when it arrives at the fault position? Nothing. Nothing will happen, because we keep in mind that this fault flash over at 4 kV, and the low voltage pulse has maybe a value of let's say 20 volts. So a low voltage pulse of 20 volts has not enough energy to bridge the air gap between the center conductor and the concentric in the pinhole in my medium voltage cable. So nothing will happen with the low voltage pulse, and the low voltage pulse will continue with its way until the end of the cable. And then at the end of the cable, we will have a change of impedance that can be detected by the low voltage pulse. So you can see this upward blip is the change of impedance. That is the end of my cable. Now, what I need to do now is find this fault. But to find this fault, I need to send not a low voltage pulse, I need to send a high voltage pulse. I need to send a high voltage pulse at least of 4 kVs. At least of 4 kVs, because 4 kVs is the breakdown voltage of this fault. Then is what I will do. I will send a high voltage pulse of 4 kV, 4000 volts, and when the high voltage pulse arrives to the fault position, there will be an arc. There will be an arc, and the arc will have a duration of milliseconds, but will be good enough in order the second low voltage pulse of the TDR find now an arc, a different situation. What we did with the high voltage pulse was to change the nature of the fault. We have a pinhole. Right now we have an arc, which means we have in temporary we have contact between the center conductor and the concentric, and now the high voltage trace will see the short, and we will have this red trace, and this red trace will inform me about the fault location of the pinhole fault. And this is the third step to do the prelocation of the pinhole fault. Once I have done with this, I will continue with the next step. But before that, I would like to show you some examples of real traces of our reflection method. In the picture in the left, you can see the typical pinhole fault. You can see that the red line is on the top of the blue one, but when we have the fault, we have the classic downward signature of the fault. In the other picture that we have in the right is the typical open conductor fault, and also we will have the downward blip at the end of the cable when we have the acute cable, for instance. Let's continue with the prelocation, just to finish, to do a brief summary. During the prelocation, there is a step. In this step, I want to learn two distances. During the prelocation, I want to learn two distances. The first one is the distance to the end of the cable. I want to verify, I want to double check what is the length of my cable. In order, I have no surprises like buried coils or a cut cable or unexpected paths. This is the first that I want to do. The second that I want to do is to find the distance to the fault, or the point where I will pinpoint the fault. So this is the two distance I want to learn. The length of my cable and the distance to my fault. And in the meanwhile, I will gain information about splices in my cable, transformers. If I have transformers in my cable, I can use them as reference to sectionalize the fault. Then let's continue with the last and fourth step, that is the pinpointing. The question is, why pinpointing? Why pinpointing? Well, the TDR, the error reflection method, can find the location of the fault. However, if I have the wrong propagation velocity, this distance will not be very accurate. Or if I don't know the path of my cable, this is other problem that I can solve with the pinpointing. Okay, so this is the reason, because we need to pinpoint the fault. So during the pinpointing, what I will do is use the tamper assisted by a pinpointing device. So what is surging? What is stopping? What I will do when I tamp in my cable? What I will do is discharge a high voltage, high frequency, high energy pulse, and I will flash over at the fault position. I will do an electrical arc. What will happen is that I will have an electrical arc when I tamp in the fault. And there are two signals that I want to pick up. the electromagnetic field or the electromagnetic signal and the acoustic signal. And we need to perform the pinpointing at least 4 kVs higher than the breakdown voltage. For instance, if the breakdown voltage of my fault is 1 kV, I should do the pinpointing or tune my cable with at least 5 kVs. So let's explain a little bit how works the pinpointing. What I will do with my source generator is that I will send high voltage pulses, let's say every 10 seconds. So every 10 seconds, I will have an arc in the fault position, and I will have two signals, the electromagnetic field and the acoustic signal of the bank of the fault, coming from the bank of the fault. And what I will do with my pinpointer is to pick up both signals. So we can say that in this case, the digiphone of Megger works under the same principle that the thunder lightning principle. For instance, let's consider that we have a storm, electrical storm. If we have an electrical storm, the first that I will see is the lightning. And a few seconds later, I will hear the thunder. So if the difference in time between the lightning and the thunder is getting bigger, this means that the electrical storm is getting away from my position. By the other hand, if the difference in time between the lightning and the thunder is getting closer, that means that the storm is coming to my position. So this is the same principle that the pinpointer, or at least the digiphone, will use. If you see in the picture, we have the guy in the position number 1 is pick up, what he did is pick up the electromagnetic signal, and 66.9 milliseconds later arrives the acoustic signal. So when he walks to the fault, this number will decrease. Now in the position number 2, we have 33.8 milliseconds, which means that the electromagnetic signal arrives, and 33.8 milliseconds later arrive the acoustic one. And when he's on the top of the fault, this number will be the minimum, in this case 12.1, and when he passes the fault, the number will start to increase. And the nice feature of the digiphone is that if you pass the fault, you will have an arrow that indicates that you need to turn because you already passed the fault. So once you're done with the pinpointer, you will be able to dig the hole and to find the fault and put on a splice or do the reparation of the cable. So doing a brief summary of the R reflection method, we can say that the R reflection method has become the favorite method for cable fault location in medium voltage cables. The R reflection method, it's a very useful method, especially in cables with insulation XLPE and EPR. The R reflection method, it's a very precise and accurate cable fault location method. And well, the voltage must be high enough to flush over the space between the center conductor and the concentric in the fault. And the energy also must be high enough to sustain the arc in the medium between the center conductor and the concentric, also in the fault. And besides utilizing the R reflection method only in medium voltage cables, this method is also suitable for high voltage cables. This will depend on the breakdown voltage of the fault and the length of the cable. So I will continue with the example of a cable fault location in a high voltage cable of 230 kV. In this case, in this fault, we use the SFX 40 kV and the digiphone Plus. Both equipments are made in Germany. So we use these equipments for the fault location. We had a 230 kV cable. The length of the cable was 4.5 kilometers. That means around 2.79 miles. We have 4 splices in the cable, and the connection point was the transition between the overhead line and the underground one. And what is important to remark in this case is that the splices of the manholes were sealed with concrete. The splices of the manholes were sealed with concrete. Don't ask me the reason, okay? So anyway, we had that situation. So if you see in this slide, in the picture in the left, you can see the connection point, that is the transition between the overhead line and the underground cable. And you can see here the lineman doing the connections of between the tamper, the SFX640, and the cable under test. In the picture in the middle, you can see the dip of the main holes. You can see that we have a plate of concrete, then we have a composite soil, and then one more plate of concrete. The dip of the plate concrete was around 30 centimeters. And you can see in the picture in the right, the main hole for the splices. So what I did first was to get my low voltage trace, and you see in this picture the low voltage trace of my TDR, and you can see that we have 1, 2, maybe 3, 4 splices. Okay, the first 2 splices and the last one are very clear. I'm not sure if this is the third one or the third one or the fourth one, but these are very clear. So this is the low voltage trace of my TDR. The next that I did was to send the high voltage pulse, and what I got was this trace. I will do a zoom in order to see more clear the picture, and you can see that I have the red trace, and at 1.76 kilometers I can see the downward blip of the fault. I will encircle in red in order to see better, but you can see here the downward blip of the fault. So this is a case in which I use the error reflection method to find a fault in a 230 kV cable. So we can also use the error reflection method in high voltage cables. It will depend of the breakdown voltage of the fault and the length of my cable. And then after I did when I done with the prelocation, I used the digiphone, the pinpointer, the digiphone to pinpoint the fault. And if you take in mind the place of concrete, the digiphone did a wonderful job because even under such conditions, the digiphone was able to pinpoint the fault, and I confirmed where was the fault. That was in the second splice. So the guys have all the assurance to break down the concrete place and do the reparations, as you can see are doing in this picture. So for finish with this webinar, I would like to do a simulation with the E-Trade products. If you see in the slide, we're seeing some of the E-Trade products we have. The E-Trade products are made in Valley Forge, Pennsylvania, and all them have the same user interface. If you see, all the equipment in this slide have the same control panel. So if you see the control panel, we have the mains on button. Then we have the control knob to activate and deactivate all the options in the display. We have the high voltage on, that is the green button, and the high voltage off, that is the red one. So I will use a software simulator, and you will see later. First, I would like to show you how I will connect my E-Trade product. In this case, I will work with the SmartTom 16. And you can see that the first connection I want to do, or I need to do, is the safety ground. Then I will connect the return of my concentric. Here you have the return of my test lead, and then the last connection I will do is the high voltage connection of the test lead. So first one is the safety ground, the second one is the return of my high voltage lead, and the last connection I will do is the connection of the high voltage. And if you see in this slide, in the right, I have the software simulator that I will use. And you can see that we replicate in the software exactly the same I have in the control panel of the E-Tray products. You can see that I have the mains on button. I have the control knob also. I have the mains, the high voltage on, that is the green button, and the high voltage off, that is the red one. I have also my keys to activate and deactivate the high voltage potential, and I have my emergency off. So I need to go out of my presentation to go in the mode of my in the software, and here I can select any of the E-Tray products we have in Valleyforge. In this case, I will use the SmartTom 60 kV. So I will start my simulation, and this is pretty much the same I will see when I am using the SmartTom 60 kVs. So the first that the unit will do is do initiate the equipment, and we will see that the first option that we have is the test. This test is encircled in red, and is where I need to start. But I would like to show you the other icons that we have in the display. We have, for instance, the TDR, that we can use the TDR for low voltage cables, for instance. Then we have the prelocation. We have also the pinpointing and the burning option. But if the unit will take me automatically through all the process of the fault location. So if I start from the beginning, I only click on the control knob to start with the first point, that is the hypo test. So I will click on the control knob, and the SmartTom will say, okay, I will do a hypo. I have other option here, that is the shift test. But right now I am doing a fault location in medium voltage cable in a fault in the insulation. So what I will do is the hypo test. So I will click one more time on the control knob, and the unit right now is ready to do the hypo test. I can of course change the voltage of the maximum voltage for the hypo test, but I will leave right now in the maximum 60 kVs. I will click one more time on the control knob, and then the unit will switch to direct, and the unit say push green high voltage on is what I will do. I will push this green button, and the unit will start to charge the cable to detect, and what we want to do is to know what is the breakdown voltage of my fault. And right now you can see here that for this example, the breakdown voltage is the 1.6 kVs. This is the breakdown voltage of the fault. So the unit click on the control knob to start the fault locating. So is what I will do. I will click on the control knob, and the unit will switch to fault locating. So is what the unit will do right now. The first that the unit will do is will send the low voltage trace to find the reference trace. And here you can see the blue trace is the reference trace, and the unit is telling me that this is my cable, and the cable is open at 940 feet. It's an open because it's the end of my cable. So if I feel confident that the 940 feet is the length of my cable, I can continue with the fault location. So I will confirm that yes, 940 feet is the length of my cable. I will confirm, click on the control knob, and then the unit did a sum in the cable, and the unit say start fault location. So I will click one more time on the control knob, and the unit say push the green high voltage on, is what I will do. And the unit will send a high voltage pulse of 60 kV to find the fault. The unit release the high voltage pulse, and you can see that we have here that fault is at 478 feet. So this is the third step, the prelocation of my fault. And the last step, the last that I need to do is take my pinpointer, take my digiphone, walk at 478 feet and do the pinpointing of my fault. I will start to pinpoint. I will click on the control knob to start with the pinpointing. And you know, the unit automatically selects the voltage of 5.6 because if you remember, the breakdown voltage of my fault was 1.6. So we need to thumb with 4 kVs or higher. So I will click on the control knob and the unit will release the high voltage pulse of 5.6 kVs every 7 seconds. So I will confirm, or I can change the time. Well, I will leave in 7 seconds. I click one more time on the control knob, and now the unit will switch to the low range and will start to thumb in the cable. The unit asked me to push the green high voltage on one more time. I will do it, and right now the unit will start to thumb in the cable and to send pulses of 5.6 kV every 7 seconds. And then I took my digiphone and I pinpoint the fault, and I'm done with the fault location. Okay, so I will finish this simulation, and I will go out from the demo software, and I will go back to my presentation. And for finish this presentation, we have the eTray products. All of them have the same user interface. We have the Easy Restore with a weight of 48.5 pounds. Then we have the Easy Thumb with a weight of 71 pounds. We have the Smart Thumb 60, and from the Valley Forge, we have also the Smart Thumb 25 that has up to 25 kVs for surge voltage and 30 kV for the DC high pot. And the weight of the Smart Thumb 25 is 270 pounds. And then we have the STX40 2000, that this unit is made in Germany. The unit reached up to 32 kV in the surge wave generator, and in high pot mode reach up to 40 kV DC. And the weight of this unit is 150 kilos. This is what we have as portable units. And if we have more, if you need more voltage, or if you need more power, of course we have our integrated test bands. So thank you. That's it. This is all what I have for you, gentlemen. Thank you very much for your attention. And Michael, it's your turn.
All right, awesome. So it looks like at this point, the presentation portion of our webinar has officially concluded. We'll take about 30 minutes to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate if you could take a couple of minutes to provide some feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or a quote on any of the Megger products you saw here today. A copy of the presentation, along with a link to the video recording of the webinar, will be emailed to everyone in about a week. You can also view recordings of previous webinars on our website at us.megger.com/webinars and register for next month's webinar, an insight into end-to-end testing philosophy. The presenter will be Sugash Cooper. All right, so let's get to your questions. All right, so the first question is going to be for Henning. Where is oil coming from in the paper insulated cable?
Okay, well, when you have what we call paper cable, the paper is not really an insulation medium. It's the oil that is the paper impregnated with that provides the insulation characteristic, dielectrics. The paper is only there to keep the oil in place. It's basically, like sucking the oil up, and by wrapping the tape around the conductor, you get your insulation. And that is why when you have a fault in that cable, you burn basically a hole in the paper, and then the hole is filling with oil that flows into that area from the neighboring areas.
Thank you. So, Robert, could you please kindly explain the physical phenomenon of bang sound appearing when certain level voltage test on fault cables?
Okay, so what is asked here is pretty much, so why do you have the sound when you apply voltage to a faulted cable? So it's pretty much the phenomenon of dielectric breakdown. So like the flashover that you want to achieve, and what Javier explained very well, that you need that flashover to make the method work. And it's pretty much you ionize this air gap, you apply voltage, and at one point the air cannot hold the voltage anymore, and it will just spark. And for a certain time, a very, very short time, an arc will be established. Current is flowing, from the surge generator through the fault back to the surge generator on the shield of the cable, and then the energy is dissipated, and the arc is gone. And because the air gets displaced out of the pinhole, that is this bang sound that you create there.
All right, excellent. While I have you, the next question is also going to be directed at you. Are the presented fault locating methods also applicable to 132 kilovolt cables?
Okay, so first of all, Javier had an example where he used a typical portable medium voltage fault location system on a 230 kV cable. So, as an engineer, the answer would be it depends. In the case of the example that Javier had, it worked very well. Now there's a little bit more to this, because 132 kV cable, that implies high voltage cables, and high voltage cables are installed in a very different way to medium voltage cables. Okay, for instance, what almost all high voltage installations have these days is cross bonding. And then you could have the case that, well, as Javier described, you are connected between a conductor and its shield on the near end, but the corresponding is kind of moving around the positions of the shields. Now, in some installations, you have the very luxury of switching the corresponding from cross-bonded to the so-called straight through. So that means in those locations, then a phase or a conductor is then associated again with a shield of a phase. But we know many installations where you can simply not even access the corresponding points. So then you cannot change that. So, and if you then have a flashover that, yes, it flashes over to a shield, but it's not the shield you connected, then you won't see anything. It's the same with the more advanced methods that you have that go beyond arc reflection. It's always the same. All of these methods that, or the methods that Javier has described in this webinar, in principle can be applied to high voltage cables, but it is always take it with a grain of salt. It's always more difficult. You have to consider more the cable construction, not just the cable construction itself, but the whole installation, the way it is made, has a big influence on how difficult it can become. And but in principle, we know this from measurements on high voltage cables that we sometimes get also, from our customers and everything, that things are possible. It's not hopeless.
Maybe, if I may chime in, one other aspect of when you have cross bonding on cables, like Robert was explaining, because you cross-bonding the neutrals. Sometimes there is a way to get around this, even you don't have access to the cross bonds, by at both ends to connect all neutrals together. We did this one time also, was also a transmission cable, 230 volt kV in Mexico, where we had the same situation with cross bonding, and we just tied all the neutrals together at the front end, and that way it doesn't matter because you have always 3 neutrals available. So we were able to do an arc reflection that way.
All right. So Henning, what does TDR and ARM stand for?
Oh, TDR stands for time domain reflectometer, because like Javier was explaining, the TDR is, many people believe it's a distance meter. It's really an impedance meter. It measures impedance in the time domain, and that's where the name comes from. So we're looking at changes in impedance along the cable, and that's where TDR comes from. And arc deflection, ARM stands for arc deflection method, because the TDR, like Javier was explaining, on a pinhole fault, the TDR cannot find the pinhole fault because we need maybe a flashover voltage of a couple kV, and the TDR signal is only a couple volts, maybe 50 volts. And so what we have to help the TDR by providing a short circuit at the fault, and be providing that short circuit by putting a high voltage on, which creates a flashover. So in the moment where we have a flashover, we're using the TDR now and shooting the radar pulse in, and the radar sees a short circuit and gives us a negative reflection. That is how that works, and that's why it's called arc reflection. Without an arc, I cannot do arc reflection method. That's what Javier was saying. If we have a dead short, there is no arc, I cannot find it with arc reflection method.
Okay. So why do open conductor faults happen in the case of aluminum only and not with copper?
Well, it's simple. Aluminum has a much lower melting temperature than copper has. Normally, where these failures, the open circuit, or we call it burnt in the clear failures happen, is when you have a circuit and there is a little bit more resistance at the point where the fault is in the conductor, but it's not enough to trip this, the fuse or the breaker. So the power is continued to be sourced to that area. It heats up and heats up and heats up, and it can melt the aluminum. And in copper, like I said, because copper has a much higher melting point, normally that does not happen. Unless you have a really catastrophic failure, then you might also get a melted copper conductor, but normally it doesn't happen.
All right. So will the thumper's location affect getting to the right position of the fault?
It doesn't affect it now, but there is a clear preference. The closer you are typically to the location of the fault with your equipment, whether it's a thumper or also whether it's, when you do the arc reflection, it's normally better to, it's easier to see the fault and to hear the fault the closer you are to the fault. That's the typical experience, okay? But it doesn't mean, if you had a fault at the very end of the cable, it doesn't mean you cannot get it. But typically what many people will do is, if they see the fault, they go to the other side and confirm it from the near side of the fault then, okay?
All right. So Robert, is the voltage of the high pot on the second step a DC voltage? If so, how high with respect to the cable-related voltage that DC voltage can be to avoid damaging the insulation?
Yeah, so Javier had two slides there. First of all, he explained in the basics this whole voltage classes, and pretty much explaining what RMS AC voltage is associated with these voltage classes, and that the actual main insulation of the cable is never stressed with this kind of nameplate system voltage, because that is face to face, but the main insulation is always stressed with like U0, like the face to ground voltage, the conductor to shield voltage, so to speak. So and what you apply when you do this this identification step, where you want to know, okay, is this a high resistance fault or is this a low resistance fault, and all the other questions that Javier brought up. That is a DC voltage. So pretty much all the fault location equipment, there's a DC source in there, which is a, you could call this a cap charger. It's a source to charge the cap, but it's also used as a DC high pot function. And this test, as Javier is explained, is carried out as a ramp test. So it's nothing prolonged, first of all, so it takes like 10 seconds. And because you start at 0, you saw it on the demonstration when he said, hey, what does a fault location situation look like? Let's say if I take a smart thumb 16, you saw this this needle going up, and then you saw breakdown at 1.6. So that was like 10 seconds. So it is not really a proof test. That's one thing. So the chances of really hurting the insulation is pretty much like not there, because a lot of people ask this question because they know now from the cable testing world that solid dielectric cable should never be subjected to DC testing anymore, because you will damage the insulation. However, that is a different test. That is a pressure test, 30 minutes or longer at substantial overvoltage. And how high you actually adjust the voltage? Well, first of all, you have your cable rating. You saw Javier's numbers. Let's say we take a 25 kV class cable that typically has an operating voltage of 14.4, but that is RMS. So it's the AC rating. Now that is associated to something like roughly 19 kV peak, right? So the cable sees at 60 hertz 120 times every second 19 kV. So if you have a 16 kV thumper for this test, just put it to 16 and let it ramp up. And because you assume it's a faulted cable, which failed at operating voltage, so that is what caused the failure. It saw operating voltage, and then the insulation gave in. So you expect the breakdown happening at a lower level. And typically on XLPE cables, like Javier explained, you expect the breakdown to be much lower, well below 12 kV. So just set it to a reasonable number. Don't overvoltage it to like crazy values, and just let it ramp up and wait for the breakdown. So you're not carrying out a DC proof test.
All right.
Maybe,
So, oh yes, continue.
maybe just a couple of comments on this. Robert pointed out, typically you do the DC hypo test at much higher voltages. The old IEEE standard called for 5 times the face to ground voltage, right? So on a 25 kV cable, you would use 70 kV DC, okay? And also the time is much longer. And I think the example that Robert used on the 25 kV cable with having 19.9 face to ground voltage, when you have a fault in the cable, you only have an air gap of about 245, or what is it, the thickness of a 25 kV cable. So, and you can roughly say, you have about 1 kV. The breakdown of the air gap is only 1 kV per 40 thousandths, right? 1 kV per millimeter. So you have maybe about 6 or 8 kV breakdown voltage, right? The fault locating voltage is really purely a function of the thickness or the size of the air gap. Has nothing to do with the voltage rating of the cable. That's very important to understand.
All right. So while we have you here, Henning, if my shield of the cable is not continuous, then how can we identify through TDR method? Or how would I know if my cable shield is having corrosion or is discontinued?
Well, that is the one big advantage of using a TDR in fault locating, especially when you have old cables, what we call the bare concentric cables that didn't have a jacket on, because it's known that these cables lose a concentric at one point and another. And like Javier was pointing out, when you're not aware of this and you do just fault locating with a thumper, you walk straight into step potential because the return current has to come back through the ground. So that is the advantage of using the TDR as a first step, because like Javier was saying, the TDR needs two conductors, the center conductor and the shield or the neutral. And if one is interrupted, the radar pulse will stop. So by connecting it, I see I have an open at a spot at a distance that I don't expect to see. The open end is much further out, so I see something I open that cannot be the cable end. So that tells me already there is a problem in the cable. And if I look where I connect to my cable and I see I have a bare concentric cable, then my first suspicion is it's probably a bad neutral. Okay. And like Javier was saying, if I have a fault now, the question is a fault in front of that open or is a fault beyond that open neutral? If it's in front, I see it right away with arc reflection. If it's beyond that open neutral point, then I will not be able to see it from that side. And that's when I go to the other side and shoot it backwards. And then I can see the fault because now the fault is in front of that open. But the TDR is the best tool to see whether I have an open neutral or not. There's no other way to ascertain that.
Yeah, just
All
to
right.
add just one sentence to that. It pretty much comes down to this whole thing of manage your expectations. You have to know, you have to have an idea how long your cable circuit is to actually, judge what you see on the screen. So if you know your cable circuit is 2,000 feet long and the situation happens that Henning described, that you have like a point of corrosion, well, as he said, the pulse suffers total reflection when one of the two conductors is not there anymore. In this case, the shield would be corroded away. Then you will get a signature on the TDR that looks like a cable end. It's a high impedance, it's an open, it's this mountain shape. And but it is not at your expected approximate 2,000 feet. It's somewhere else. And if you know, hey, I have unjacketed cable, that's a strong indication that there might be something going on with the shield.
But there is also always another way to verify this. If you see an open and you're not sure, is it the end? Is it an open, is it an open conductor or it could be an open neutral? If you don't know, you go to the other end and you short the conductor to the neutral. If you see no change on your TDR screen, you're not looking at the cable end, but you must be having an open, either open conductor or open neutral. That is the confirmation of that situation. So, if you have a short URD cable, most people probably won't go through that step. But if you have a longer feeder cable where it's important, you might want to do that step because it takes the gray out of your the answer. You need black and white answer when you fault locate. Is it an open? Is it not an open? Okay, and there are ways to do this with using the TDR actually.
All right then. The next question is going to be towards Robert. How do you find the face-to-face fault in TDR?
Well, first of all, as Javier described, that depends on if a fault like this can even happen depends on the cable construction. It's pretty much impossible that on a 3-core shielded or screened cable you can have such a situation. The next thing is for 3-core cables, specifically the belted cable, the phase comparison is always a very, very strong method. And depending on your equipment that you have, you know, more modern equipments, they have this insulation resistance function built in, even in an automated way. So if you connect your 3 cores, you can measure actually all 6 pairs, you know, the 3 phases to the neutral and the 3 face-to-face situations at once, and you get in a few seconds a very clear picture of what's going on. And so that is one thing. So phase comparison can be used. And the other thing is simply, if you want to measure a face-to-face condition, you have to be connected face-to-face. If it's really you know, from let's say A phase to B phase or something like that. But then keep in mind, Javier very you know, well explained the limitations there. The TDR can see very low impedance situations, very high impedance situations. One example was this burned in the clear that Henning described, that, you know, where, you know, the cable is pretty much destroyed at this point. But the pinhole fault, so any kind of you know, in between situation that is high resistance, so that the fault does not show any physical reaction to the 50 volts, or maybe if you have a high-end radar, 160 volts of TDR. If that is not enough to you know, get a reflection back, then it won't show up on the TDR trace. That's the whole motivation to have the arc reflection method, because TDR just by itself, low voltage TDR, is blind for high resistance faults.
Maybe I like to add one little caveat to this. Okay, if you have a single conductor cable, you're absolutely right. You can only see either an open or a short circuit with a TDR. But if you have multiple conductors, especially like if you would use a TDR also on, let's say, triplex cable, on low voltage cable, there, because it measures the impedance, you can compare the impedance between different pairs. And there you don't need an absolute open or short. Just the difference in impedance between 2 pairs is a giveaway where the fault is. It works excellent on low voltage cables.
All right, it looks like we have time for just one more question. So Henning, to check the breakdown, which source is more efficient, AC or DC? Is there a relevance to the high cable voltage test that has been carried out with the DC because it's been Earth systems anyways?
Well, more overall, I think it's fair to say, the more effective cable test is an AC test, because just simply because of the fact, because you have changing polarity. That change in polarity, because it happens at such a fast rate, like, you know, that was at 8 milliseconds or whatever, it puts a lot of stress on the cable. It's not just the voltage stress, it's also the change in the voltage over time that stresses the cable quite a bit. That's why you can see when you compare running a DC test on a cable to a, let's say, AC, which is today basically a VLF test, and you would use the same voltage, let's say you use 20 kV DC, and you would use, let's say, a peak voltage of 20 kV AC, the AC test would flush out more problems in the cable than the DC would be, because it's a higher stress. So overall, it's a preferred method to, and you can see that also when you do a test and you have a test failure, which can happen. Typically, the fault resistance when you did a VLF test is lower than when you did a DC test. So it's already easier to fault locate typically when you had a VLF test before than when you had a DC test before. No?
Yeah, just to add to this a little bit, because the one part of the question also asks about the breakdown again, okay? When you do the fault location, going back to the stepped sequence, you use DC, because cable fault location equipment doesn't have an AC source. The basic source to execute all the high voltage functions is your DC source, charging the cap, the burner and everything. So in this case, you only have DC available. And this is why you would do that step with DC. And you can see the difference when you do fault location. That's a whole different premise. Henning just explained the cable test, the withstand, as it is heavily regulated in various standards. But in the fault location, I mean, in the simple system, or in the most simple fashion, you have like a small cable fault location system with you, maybe one of these micro thumpers, and that has multiple fault location methods, and its source is a DC source. So you have to do this first step with as a breakdown test with the DC source.
The DC source has one other, let's say, on a breakdown test, because breakdown test means I have a fault, okay? So I have somewhere an air gap in the medium voltage cable. And when you apply DC, you always have this additional effect of ionization of the air. So as you keep the DC voltage on, the air starts to ionize, and then the air breaks down earlier at a lower voltage and flashes over. Okay, so the fault locating application for DC is very different than the test functionality. Okay.
Okay then. So it does look like that's all the time we have for it. We apologize if we didn't get your question today. We had so many great questions, but we will try and follow up with you in the next couple of weeks offline. Thank you all so much for attending. If you could please remember to answer the survey. The survey will also include a field for you to request a quote or a demo if you're interested. A copy of the presentation, a recording of the webinar, and your certificate for attendance will be sent out in about 2 business days. Once again, I thank you all for attending, and have a great weekend.